Solution concentration. We've talked about solutions. We make them at home all the time. If you take some table salt and mix it with water, it seems to disappear, right? It becomes part of the liquid, but we can tell that it's still there when we taste the water, right? It's a homogeneous solution. If we taste it, we taste the water, taste the salt. If we boil all the water away, the salt will still be there. We call homogeneous mixtures solutions. Typically, you think of a solution as being something that's a liquid, but it could be anything. It could be a gas or a solid. So there are two parts to a solution. There's a solvent. There can only be one solvent. It's generally the thing that there's more of. Another way to decide is the solvent keeps its state, whereas the solute may change its state. The solute is present in lesser amount. There can be more than one solute. So you could take that cup of water and put some salt in it. The salt was a solid. The mixture, the solution, ends up being a liquid. Water is the solvent. There's more of it, and it remains a liquid. Salt is a solute, and it changes its state. There's less of it. We could also put a teaspoon of sugar in there and stir it, and sugar would also be a solute. Okay? Solutions are mixtures, and so the composition can vary. You could put in another teaspoon of salt or half a cup of sugar, right? And it would still be a solution, but it would be saltier or sweeter. Pure substances have constant composition. They always have the same relative amounts of components. So to describe solutions accurately, we need to describe how much of each component is present. A pure substance such as water or octane, we can just use a single name because it's always the same. But with a with a mixture, a solution, we need to describe what's in it and also the relative amounts. So we have some qualitative terms to describe solutions, and the words dilute and concentrated, and these mean the same thing that you think they mean from everyday life. Dilute means there's a small amount of solute compared to the solvent, and a concentrated means there's more. So you can go to the grocery store and you can buy, some cleaner to clean the bathroom, right? It comes in a spray bottle, is ready to use. And typically right next to that, there are bigger bottles of concentrate, right? So you could buy one of those, and when you use up the first bottle, you put a little bit of the concentrate in the bottle and then add some water, and then you've got more of your original cleaning spray. It's concentrated, it just has more solute particles in it and less solvent than the dilute one. So that can be useful, but typically we want some numbers associated with this. So a common unit we use in chemistry is molarity. So molarity, and it's abbreviated with a capital M. Molarity is defined as the amount of solute in moles divided by the volume of the entire solution in liters. So molarity is the amount of solute in moles divided by the volume of the solution in liters. So the units of molarity are moles per liter. Here's an illustration of making a solution with a particular concentration. This would be a 1 molar NaCl solution. So 1 molar means 1 mole per liter, 1.00 moles per liter. So the entire volume of this solution is a liter, and so we need to put 1 mole of the sodium chloride into it. So we would use the molar mass of sodium chloride and determine that it's 58.144 grams. So we would measure out that mass of sodium chloride, and we would add water. Typically, you would add water up to about here so that you would still have room to swirl it around and mix it, because you want all of that solid to dissolve before you fill up the neck, because once you get it up into here, it's really difficult to mix it. So this is a volumetric flask, and it has this tall, skinny neck, because in the tall, skinny neck, a couple drops of water are going to make a difference in the height. And so it's going to be more precise and more accurate than if it was something like a beaker or even a graduated cylinder. So you fill this up so that the bottom of the meniscus is right at the mark, and then you know your volume precisely. You would then put a stopper on this, and you'd need to mix it well. And typically we invert it to mix, and 10 to 20 times to get it thoroughly mixed. So let's do a calculation. Calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. So they're asking for molarity. So here we need to use an equation. So molarity, abbreviated capital M, I always underline my capital M's because I don't take the time to make them pointy. So molarity equals the moles of solute, and here our solute is sodium nitrate, divided by the liters of solution. So that's SOL''N, chemist shorthand for solution. Do we know how many moles of sodium nitrate we have? Was that given to us? They gave us the mass, right? Can we calculate the moles from that? Sure we can. What about liters of solution? Did they give us that? Yeah, they did. A total volume of 2.50. So 2.50 liters, we've got that part, but we need to find the moles. So we're going to have to do a unit conversion on the side, 45.4 grams of sodium nitrate. And I want to find out how many moles of that there are. So I need the molar mass. So 22.99 plus nitrogen plus 3 oxygens. And my calculator is giving me 85. Is that exact? No. It's a whole number. How many significant figures should that result have, though? It should probably have 4 sig figs or 2 decimal places, which ends up being the same thing. But why doesn't it have any decimal places? Because my calculator has no idea what sig figs are. It doesn't know. So I need to recognize that and say, oh, well, this should be 85.00. It doesn't happen like that very often. It's like going to the grocery store and your bill comes out to exactly $100. You're like, what? You couldn't do that if you tried, right? Just happens every once in a while. This is one of those. So 85.00. 45.4 divided by 85. 0.53. I should have 3 sig figs here. 1 moles. I'm not going to round this because I'm going to continue on with this calculation, and if I round it, I could introduce errors, and I don't like that. I still have the entire number, 0.534117647, in my calculator. Instead of typing it in again, I'm just going to use that number. Divide by 2.5. I should still have 3 significant figures here. 0.21364. So that's going to round to 0.214. And the units here, capital M for molarity, or 0.214 moles per liter. They mean the same thing. Any questions? Yeah.
What's the number between the mole of sodium nitrate?
This number?
The one on top.
That one?
On top, sorry.
Up here?
Under mole of sodium nitrate?
This one?
Yeah.
Okay, that's a sloppy word. Let me do that a little neater. SOL apostrophe N.
Oh.
Solution. Thank you for asking. Any other questions? Molarity and moles are not the same thing. Okay? They're not the same thing. I had students in my 1B class in the spring that were just very, very confused about what molarity was. And that gave them a lot of problems. So we can use molarity as a conversion factor in problems. It relates the moles of solute to the volume of the solution. So let's do an example here. How many grams of sucrose are in a 1.55 liter, are in 1.55 liters of 0.758 molar sucrose solution? So solving problems, going for dimensional analysis is always a good first approach. Sometimes you have to use an equation, but a lot of times you don't. So let's pull the numbers out and write them down. So I have 1.55 liters, and then I have this number 0.758 with a capital M. So the capital M probably doesn't really say much to you. So when you write this down, write down the units that stands for. 0.758 moles per liter. That is what the capital M means. So I have liters and I have moles per liter, and then I look to see what am I asked for. I'm asked for grams of sucrose, C12H22O11. So I'm going to start with one of these numbers, and I'm going to convert to grams eventually. Well, this one could be used as a conversion factor. This one, come on pointer, this one cannot. So let's try starting with the liters and make use of this as a conversion factor. So this would allow me to convert my liters to moles. So I could do liters to moles. It's moles of the solute, which is the sucrose, and then how do I get from moles of that to grams? Molar mass. So 2 steps. 1.55 liters of solution. I want moles on top. I'm going to put liters on the bottom so those cancel out. And then I'm going to go grams and moles on the bottom. It's grams of sucrose. There's not a chemical reaction occurring here, so the substance isn't changing its identity, so you can be a tiny bit slacker and just leave off the formula. This mole to moles and liters relationship is the molarity. So 0.758 moles per liter. Here I need the molar mass of sucrose, which I'm going to have to calculate. So I've got 12 carbons times 12.01, 22 hydrogens, and 11 oxygens. It's 346, but I don't trust my memory. $342. So 342.296. And again, I'm not going to bother rounding that because it's not going to really matter at all. And keeping more digits is not harmful. So that's the mass of 1 mole of sucrose. So I've got 1.55 times 0.758 times 342.296 equals. My starting number had 3 significant figures. My molarity had 3 significant figures. This had at least 3, and so I'm going to have 3 sig figs in my answer. 402.16, which I will round to 402 grams of sucrose. Any questions?